Sir, you go in the the central area and then let the bar pop up, and that will show you the sign of a mic which you have to unmute.
Okay. Can you
Yeah.
hear me? Yeah.
Yes. Perfectly, sir. Good morning, sir.
Good morning.
Yeah. Are you all set to go ahead?
Yeah, almost I am ready. And should I project now my
Yeah. Let us keep it.
projections?
Yeah. Let us keep it projected, and then I'll introduce you before you begin. After that.
That's okay.
Yes.
Can you hear? It's okay? Please go ahead.
Perfect. Everything is perfect. No problem.
Yeah.
So you project your material.
Yeah, it is there.
You have to present it, sir. We are unable to see it.
Okay. Well, that pop-up again will come?
Again, that pop-up may you have to go and then present now.
Yeah, just a minute. Pop-up.
Yeah.
Pop-up.
If you go in the main area, the horizontal bar will pop up. Catch that bar. Go to present now.
No, I think that's not coming, guys. That pop-up is not coming. So how is that pop-up will come?
Yeah, if you take your cursor completely outside the screen area and then bring it above, it comes up.
Okay. No, it didn't come. It simply actually changed my screen. Okay.
No. You have to be in Google Meet. Open the Google Meet fully. Let your screen be occupied with Google Meet only fully.
Okay.
Yeah, then you will be able to see us and yourself there.
Yeah. Okay.
Yeah, now you go in the main area of the screen and you catch that present now thing. Yes.
Yeah, it is present now. It is present now.
And then go to that, your entire screen. Your material is open, na?
Okay. Yeah.
Yeah, so you just do that. Your screen will be shared with all of us.
Okay. Share, na? I have to do that share?
Yes, sir. Entire screen. And then, share that inside the window, share mein click kijiye. Then it should start doing. Yes, it is doing it.
Yeah.
It has appeared, but you are in the middle, I think. You have to go to the upper pages where you have to begin, I guess.
Yeah. Just a minute.
Sure.
Okay, it's starting.
Yes. This is from where you are going to start. So, let's be ready. I'll just give the audience, your brief introduction, and then you can begin the session.
Okay, thank you.
Yes, sir. Dear participants, it's my proud privilege indeed to introduce to you today's distinguished speaker, Dr. Surya Kumar Maiti. Professor Maiti got his BE in Mechanical Engineering from Burdwan University in 1970, and he came out as a gold medalist there. Okay, so the beginning of the illustrious career began right in 1970s. Later on, with government scholarship, he went for MSc to Birmingham University and completed it in 1973. He joined actually meanwhile IIT Bombay, and then while he was working at IIT Bombay, he registered as a research scholar under his own guidance. There was no provision then those days to have a formal guide from anywhere. So he was his own guide, and there was no guide in a sense for his PhD. He completed such a PhD in 1980 while he was working there as a faculty member, and then subsequently he went for attending the prestigious doctoral fellowship from Cambridge University for 2 years, starting from 1981 to 1983. His experience involves, research and industry all. Initially, he worked as a research fellow for 1 year in CMERI, Central Mechanical Engineering Research Institute, Durgapur. After that, he has also, to his credit, experience as a design engineer in Tata Motors Jamshedpur from 74 to 75. And after that, he joined IIT Bombay, and there onwards his academic career started, and he rose from the initial position to the post of the professor of IIT Bombay during the span of starting from 1975 to 2009. In 2009, he was awarded G.K. Devarajulu Chair Professorship, which is also a very prestigious chair. In the year 2019, on which he continued to work for 3 years. After that, he was working as Emeritus Fellow from 2012 to 2018 in the Mechanical Engineering Department of IIT Bombay. He was invited as Emeritus Fellow to guide teachers and students, teach some students there at IIT Bhilai for 1 year's time. And he has recently completed that assignment also. Meanwhile, he has been elected as Professor Emeritus at IIT Bombay, a very prestigious position. He has also been visiting professor to National University of Singapore in the year 2010 to 11. He has several awards to his credit. He has got Excellence in Teaching Award in 2006 of IIT Bombay. He is Fellow of the prestigious National Academy of Science of India, Fellow of American Society of Mechanical Engineers. He is only the 6th Indian to get this fellowship. Then, he is actually Fellow of Indian National Academy of Engineering also, which is also a very prestigious academy. And he is reviewer of several, national and international journals. His area of interest and research include fracture mechanics, finite element methods, boundary element methods, composites, and component health monitoring. While his long career, more than 40 years of teaching career at IIT Bombay, he was instrumental in developing several undergraduate and postgraduate courses: solid mechanics, strength of materials, finite element and boundary element methods, pressure vessel design, fatigue fracture and failure analysis. Advanced finite and boundary element methods are the few courses to name here. He has also been recorded for a very, very coveted NPTEL course on advanced strength of material. He has widely published in international journals, and he has more than 125 papers to his credit. He has also guided more than 22 students in his entire career at IIT Bombay, and I happen to be one of his students. He has also authored a book on fracture mechanics, fundamentals and application recently, which has come from a very prestigious publisher, Cambridge University Press. So, I am very proud to welcome a great teacher and researcher for this session, and I just hope that all of you benefit from his knowledge and experience as much as I have been benefiting. With this brief introduction of Professor Maiti, may I request you to take over your first session on introduction to theory of elasticity. Professor Maiti.
Thank you, Sachin. It's really very proud moment, and it is certainly actually exaggerated picture by my student, dear student Sachin Naik. So please just forget about all that. My present job today is to just talk before you some introduction to two-dimensional elasticity. I think the course actually is named Product Design using Finite Element Method. So therefore, I have to really talk something about just product design and then move quickly to usage of finite element method. See, obviously, we are all mechanical engineers. For that matter, any engineer has the primary responsibility of designing machines and systems of variety of kind. And in that process, we have to do analysis for doing the right type of design as required in the system. And for that matter, we have to really do analysis. And this analysis always involves a lot of calculations. And particularly if you talk about mechanical engineering design, we have to do stress analysis, which is quite basic to design process. And therefore, we do a lot of calculations, and when it becomes system becomes complex, it's not possible to manage these calculations by hand, and therefore we have to take recourse to computer. And it has come very handy these days that we do all calculations mostly by computer, and this can be done fast and also done repeatedly with whatever changes we would like to introduce. And that way it has become very useful. And obviously, that product design, obviously, whenever you are designing a product, you try to actually try lots of variety of design and uh, arrangements, and therefore you do actually variety of calculations for the systems with varying parameters and dimensions. And therefore, you see that this can be very easily done using computer, and that's how it has become very fast these days. The competition in the market is extremely fast. Everybody wants to bring in new product and reduce the cost, and therefore people have to do calculations using variety of materials and also variety of changes in the system, existing system, and all new systems must be quite up to the expectations of customer, and therefore varieties of things have to be introduced. Therefore, parameters that are involved in the design is actually wide, and this cannot be done easily by other than using computers. And therefore, computer is handy, and therefore we make use of all software and all the calculations that are needed in the process by computers. Obviously, one of the important calculation for mechanical design is strength calculations and functional design, and therefore you see you do a lot of changes so that you come out with the best product, and it has minimum cost, minimum usage of materials and manufacturing cost, and therefore these are actually quite standard. And therefore this can be easily done by using, hello, is that okay?
Yes, sir.
Yeah, thank you.
Yes, sir. Yes, sir. No problem.
Thank you so much. So therefore, you see that we have to make use of calculations. Particularly, we have to do the strength analysis, which involves at the core is actually stress analysis. And this stress analysis is possible these days using varieties of numerical methods and software packages. And these software packages consist of really calculations which are in programming language. And finite element is one of the important methods. So also the other method that are used in stress analysis are boundary element method, then meshless method. That nowadays varieties of methods have come. Finite element is a discretization based method, but then it is not always necessary that you have to discretize the whole body. You can also do just analysis of the whole body by considering the boundary geometry, and which helps in the analysis. You think of it, if it is a two-dimensional body, then you just simply analyze the things at the boundary. So it reduces the dimension of the problem. Similarly, if it is a three-dimensional problem, then you just analyze the surfaces, so it becomes a two-dimensional problem. So you see, these are the advantages of the varieties of methods. And now, coming to today's discussion, my job is to really, first of all, talk about what is stress analysis and what is the mathematics involved in the stress analysis. Basically, you talk of any area, you talk of stress analysis, there are certain procedure of analysis, and finally it boils down to differential equations. You see, all that you do is to write the differential equations about the deformation process. Similarly, if you are trying to talk about, let's say, fluid flow, then you also write the differential equations, which is Navier-Stokes equation, that is momentum equation, then continuity equation, then energy equation. So these are the equations which are written in the form of differential equations. if you are trying to think in a simplest sense, that if you think of heat transmission, that is actually transmission of heat, then in that case it is actually going to have differential equations. If it is unsteady state, it will have some form. If it is steady state, it will have some other form. And these differential equations, again, its dimension, its complexity will vary depending on the dimension of it. If it is one dimensional, then it is simple one degree equation, one dimensional equation. If it is second degree equation, then it is going to be actually again involving two variables. So it is two-dimensional equations. Similarly, in three dimensions, you have this differential equation form will change. And now let's think of the equations that are involved in the deformation process and therefore stress analysis. So that's what I would like to spend some time before you about talking about the two-dimensional analysis of stresses using the exact methods. Now think of it, how do you define the problem? Basically that stress analysis, which I would like to define again, you think of this first slide. You see that if you are trying to think of a problem of two dimensions, which is shown in the left, so you have a two-dimensional geometry which can have simple geometry, which can have complicated geometry, rather actually non-linear geometry. And look at this case. So in this case, you see that you have the geometry which is not defined in terms of the simple shapes. And now what is that we have to do? We try to define the geometry in using coordinates, rectangular coordinates like x and y, and then we have some forces acting at its boundary, which are shown schematically. There some forces are there, and the body is in equilibrium, and it is going to deform under the action of forces, and therefore what it means that every point of the body will have displacements in the x direction and y directions. And here we would like to represent the displacement in the x direction by u, which is a function of x and y. Similarly, v is the displacement in the y direction of a point like P, and it is also a function of x and y. So therefore, if you are going to solve this problem, you have to solve finding out the displacement at every point of the body under the action of these boundary forces, which are keeping the body in equilibrium. So that's the problem. So therefore, you have to find out the displacement at every point of the body in the whole geometry under the action of the boundary forces. Now, alternatively, you see that we can also state the problem like this, that at every point of the body, like P, we will have some stresses. It is going to have stresses like sigma x, normal stress in the x direction, sigma y, normal stress in the y direction, tau xy is the shear stress at any point, and exactly the, I have another shear stress which is tau yx. Will show just shortly that these two stresses are the same. So therefore, you see, we have to find out the stresses, three stresses, sigma x, sigma y, tau xy, which are all functions of x and y coordinates. And we have to find out these three functions, sigma x, function of xy, sigma y, a function of xy, tau xy is also a function of x and y. So therefore, you see that I have shown these stresses schematically at a point here in this sketch. You see, that is the point, and then how do you actually show these stresses? So if you just generally to represent the stress state at a point, what we consider a square, infinitesimal square enclosing the point P, and then this square has four faces. You see that this face, which is on the right vertical face, it is actually called x face. Its outer normal is directed in the x direction. That's why it is indicated by x face. And the stresses that can act on this phase, that can be two stresses at the most. Normal stress, which is indicated by sigma x, or sometimes it is also indicated as sigma xs. And then this stress which can act parallel to the phase, x phase, it is actually shear stress, and it is indicated as tau xy. This x indicates the phase on which it is acting and the direction in which it is acting indicated by the second index. So these two initial notations is very convenient for two-dimensional stress analysis. I must tell you that this normal stress, which I have represented as sigma x suffix x, it is in fact actually sigma xx. This is the stress acting on the x phase in the x direction. So therefore its actual notation is sigma xx, and generally, for these cases conveniently it is written as sigma x for normal stress. Whereas for shear stress it is always written by two indices. One, the first index indicates the phase, x phase on which it is acting, and the direction, second index indicates the direction in which it is acting. So therefore, by this logic, you can immediately understand the phase which is actually having outer normal in the vertical direction or y direction. Normal stress is sigma yy, but we write it in a short form sigma y, and the shear stress, it is y phase, and shear stress which is acting in the positive x direction, it is indicated as tau y phase, x is the direction, positive x direction. So therefore these are the four stresses that comes up on these two phases. Now you think of it, the phase which is on the left, vertical phase, its outer normal is directed in the negative x direction. So it is actually negative x phase, and the stress which is acting in the negative x direction, it is called positive stress, and it is actually indicated as sigma xx, or in short sigma x. Similarly, the shear stress which is acting on this x phase, it is actually acting downward because it is acting in the negative y direction. So therefore it is also indicated as tau xy because it is negative phase acting in the negative y direction. It is also indicated as tau xy, and it is actually also a positive stress, positive shear stress. As we have indicated that tau xy is a positive shear stress on the positive x phase, similarly this tau xy is also positive shear stress. It is acting on the x phase, negative x direction, and negative y direction. These both negative, it makes it again actually positive shear stress. And similarly, the bottom phase, which is actually y phase, is negative y phase, and its outer normal is negative y direction, and the stress which is acting in the negative y direction, it is indicated as positive normal stress, and it is sigma yy, in short sigma y. Similarly, the shear stress, it is acting in the negative y phase, and therefore first index indicates the phase, the outer normal, and then second index indicates the direction, negative x direction, so therefore tau y. So it is also a positive test. Both negative makes it positive. So these are all positive stresses. So that's how you see that you will shortly see that this tau xy and tau yx, they are same. Finally, we find that for giving the stress fully at a point, we have to determine sigma x, sigma y, and tau xy, and which is same as tau yx. So these are all positive stresses. And the extension of this sort of approach to 3 dimensions is given on the right-hand sketch, and you can, I think you can appreciate it very easily. I give you a minute to appreciate. You see that in 3 dimensions, we consider a unique cube enclosing the point, and then it has actually 6 faces. So the positive x face, which is on the right vertical face, You see, it's outer normal in positive x direction, and this normal stress is sigma x. Shear stress in this x phase, you can have shear stress parallel to the y axis. That's why the vertical stress which is shown there, it is nothing but actually tau xy, and the other stress which is acting on the x phase but acting in the positive z direction, it is tau xz. So therefore, in 3 dimensions, you see on a face, you are going to have 3 stresses, 1 normal stress and 2 shear stresses. So exactly the same way, if you consider the top face, top horizontal face, it's positive y phase, and the stress which is acting in the positive y direction, it is sigma y stress, and on this y phase, the shear stress which is acting parallel to this phase, it is tau yx, y phase, positive x direction. Similarly, the stress which is acting on this positive phase in the z direction, it is indicated as tau yz. So therefore, you see that on each of the phases, you have 3 stresses. Now coming to the last phase, which is actually positive z phase, is outer normal is positive z, because we have taken the z axis to be in this direction. So therefore, look at this. It is actually positive z axis, and therefore the normal stress which is acting in the phase z phase, and in the z direction stress is acting, it is sigma zz, but in short we have indicated it as sigma z. Similarly, the other stresses, you see that which is acting on parallel to the phase but acting in the positive x direction, it is tau zx, z phase x direction. Similarly, stress which is acting in the vertically upward direction, it is tau zy, z phase y direction. So therefore, you have all these stresses, and if you just consider the negative phases, again you will have actually 3 components on each of the phases. Finally, we'll find in this case total number of stresses that are actually there is nothing but sigma x, sigma y, sigma z, tau xy, or again tau yx, tau yz, which is same as tau zy, and tau xz, which is same as tau zx. So therefore, see, in this case, you have 9 components of stresses, but because of the fact that tau xy is equal to tau yx, tau yz is equal to tau zy, similarly tau xz is equal to tau zx. Finally, what you have 3 normal stresses, sigma x, sigma y, sigma z, and 3 shear stresses, tau xy, tau yx, and tau zy. Zx, I'm sorry, tau zx. So therefore, tau zx, so these are the 6 stresses which are actually acting at a point, and each of them is a function of coordinates x, y, z. So see that in 2 dimensions, they were all functions. We had 3 components of stresses, sigma x, sigma y, tau xi, which is on the left, and on the right hand side, we have sigma x, sigma y, sigma z, and tau xy, tau yz, tau zx. So 6 components of stresses. So the problem is much more involved in 3 dimensions. Now the question is, how do we determine these stresses? You see that this deformation of a body, it is governed by certain laws or equations. So this deformation process we have to write in the form of equations, differential equations. So mathematically we try to write in the form of differential equations, and they are the basis in determining the values of the stresses at every point of the body. So what are they? You see that since the body which is under consideration, this body is in equilibrium, you see that each point of the body, if you just try to consider an infinitesimal element enclosing that point, since the whole body is in equilibrium, even that infinitesimal element is also going to be acted upon by stresses on the boundary of the element, and they are going to be in equilibrium. I repeat again, you see that you think of it, a point means you have to think of that it's a square enclosing the point in 2 dimensions, or in 3 dimensions. A point means that it's a cube, infinitesimal cube enclosing the point. So therefore, you see, if you just try to take that element, small element out of the body, then obviously on each of the boundary, the forces are going to be acted upon by remaining part of the body. So that's what actually that particular element is acted upon by stresses or forces on its boundary, which is subjected by the rest of the body. And obviously this element, infinitesimal element, must be in equilibrium. Since the body is in equilibrium under the action of the external forces, this infinitesimal element is also going to be in equilibrium under the action of stresses which are acting on its boundary. So that's what is the typicality of the body under deformation. And you see that we have shown this element under stresses. These stresses are acted upon by the remaining part of the body. So at the common point or faces of this element and rest of the body, forces are acting, and these are shown here. Since it is small, we are showing it like this, but if it is actually of large dimension, it will have actually some other variation. Similarly, in 3 dimensions, you look at this element which you have segregated from the rest of the body, it is subjected to stresses on each of its faces, which are applied by the remaining part of the body. And therefore, you see, this particular element which is isolated must be also in equilibrium. That's the point. And that's what is the basis for writing the deformation equation or deformation rule of the body. And you see that I would like to show you how we get that equation. This equation, always in the form of differential equation, will show you how we get that. So for the moment, I'll come down to 2-dimensional body, and therefore we'll isolate an element which is infinitesimal of dimension of infinitesimal element of size. You see, its size is a square element whose vertical side having dimension delta y and horizontal face has dimension delta x. So that's the element we have isolated from the rest of the body. And you see that the stresses that are going to act on its boundary. So if we consider on the vertical x face, which is of the left end, if the stress acting, this delta x and delta y are very small size, and therefore if we consider the stress acting on the face delta y, vertical face on the left, it is going to have, we consider it is such a small element, the stress intensity is going to be sigma x. So the stress intensity that is acting on the vertical face on the left hand side, it is sigma x, that's what we have written. And the shear stress, its intensity is also uniform, tau xy, that is the stress, shear stress. Exactly following the same rule, the stress acting on the bottom face, which is negative y face, here the stress intensity in the y direction is sigma y, and shear stress intensity is tau yx. Now you see that if I move from the left face to the right vertical face, look at that, I am moving by delta x, and therefore we cannot expect that the stress intensity on this face will remain the same and it will continue till the other end, which is at a distance of delta x. It cannot be. So there will be some changes in the value of sigma x and tau xy. So what we do is that we write the stress intensity on the right face, vertical face, is going to be sigma x plus some change in increment in the sigma x, which is delta x. Similarly, the shear stress, which was tau xi on the left vertical face, on the right vertical face, it will change, and we will write that tau xi plus some change delta tau xi. As I move by delta x, it's going to have changed. And therefore, you see that we write this delta x. What is that delta x? It is nothing but, it's written here, delta x is nothing but rate of change of x with respect to x multiplied by distance delta x. So delta sigma x that I have written, it is nothing but this quantity, delta sigma x, delta x, delta x. And similarly, tau xy,
Excuse me, sir.
yeah.
There is some, one window that has come. You have to close that. Yes, thank you. Please.
Okay. That's okay now? Okay now?
Yes, sir. Perfect.
Hello?
Yes, sir. It is okay now.
Yeah. So now you see that the sigma x trace which was acting on the left vertical face, it has changed to value delta sigma x. On the right vertical face, it has become sigma x plus delta sigma. And this delta sigma x is given by here delta sigma delta x multiplied by del x. So that's the increment. Similarly, tau xy, which was acting on the left vertical face, it has undergone change on the right face, which is given by del tau xy, and this del tau xy is given here delta tau yx, delta y, delta y. I'm sorry, it is same thing as delta tau xy equal to delta tau xy delta x plus delta x. That's the way we have to read. So that's how it had changed. Similarly, if we consider the equilibrium of the whole body in the x direction, before that I would like to bring something else. You see, this particular element can have some local forces. I think this is something very important for all of you. Please understand that there can be body forces, there can be local forces in the body. What is that? Suppose you are trying to analyze a structure under gravity forces. This external load will be explicitly given by the situation, but the self weight of the body, that is also going to give some force. So you think of it that you have a column, very large column, and now when the wind forces are acting, it is subjected to forces which will give deformation under the external forces. But at the same time, you think of it, if it is a large vertical column, it will have at every point some load, which is the load due to the self weight. As you move from the top of the column to the bottom of the column, your load at every point will have different intensity. Like, you think of it when you are at the top of the sea, you will have some load, but then as you go down, whether it is let's say it's a submarine, when it is at the top, it will have loads because of the internal pressure, but as it goes down, you see, it will have not only those forces due to the pressure inside, but at the same time, you will have also load due to pressure of the sea water. See, that sea water pressure will be active. So therefore, you see, these are going to change depending on the position. So that's the way it is, that in the case of the forces which are due to self weight of the body, they will also act at a point. So that is indicated here by capital X and capital Y. These are called volumetric forces or body forces. These are due to actually volume of the element the forces are going to act. So these are due to self weight. But I think I must bring you another example of these body forces or volumetric forces. What is that? You think of it when a wheel is rotating. You see the turbine wheel. When it is rotating, the load is acting due to pressure of the, let's say, the pressure, external pressure of the gases or forces due to flow and all that. But at the same time, you are going to have, if it is rotating, then it will have centrifugal forces. So therefore, you see that in the case of rotating body, when a grinding wheel is actually just rotating, if it is stationary, it will have just weight at every point. But then when it is rotating, you see, it will have also centrifugal forces. It is going to have forces which is going to vary from the center of the wheel. As you go to the outside, the centrifugal forces are going to vary. mv square by r. So therefore you see that centrifugal forces are going to change depending on the radial position. So that's what it is. So when you are trying to find out that what are the forces in the grinding wheel when it is rotating, then you don't have actually any other forces but the centrifugal forces. So there in that case, you don't have any external load acting other than these centrifugal forces. So you want to analyze the grinding wheel when it is rotating. You have to bring in these body forces, which are indicated as volumetric forces. Capital X is the body force per unit volume. Similarly, capital Y is the body force per unit volume, and X is in the X direction per unit volume, Y is in the Y direction per unit volume. So these are also to be considered when we are trying to consider equilibrium of the body. So therefore, you see that when we try to write now the equilibrium equations, you see that if I try to consider now this element of size delta x, delta y, let's assume that the thickness of this element, it's a disc-like, and its thickness in the z direction is t. So therefore, you see that what is the force? The force due to sigma x plus delta sigma x, it's written there. It is actually sigma x plus delta sigma x into the area delta y into t, acting in the positive x direction. And similarly, from the left face, sigma x multiplied by delta y into t is acting on the negative x direction. So therefore, this is acting in the positive x direction. This is positive y direction. Then again, we have the force acting from the shear forces. Look at this. We have the shear stress tau yx plus delta tau yx acting on the vertical face, whose size is delta x multiplied by t is the area. So therefore, you see that total force acting in the positive x direction is tau yx plus delta tau yx multiplied by delta x is into t is the area. And if you try to go to the bottom face, it is actually acting. It is acting in the negative direction. I'm sorry, this sign is actually wrong. Tau yx is acting in the negative x direction. So therefore, it is negative direction. Therefore, you see this is positive x direction. This is positive negative x direction. So cancel, plus the body force, which is x acting in the capital X per unit volume in the x direction. So therefore, total force is x multiplied by the volume of the element is delta x multiplied by delta y into t equal to 0. So this is the equilibrium equation of all the forces that can be acting on this element. And if we consider the situation that when this size of the element delta x, delta y shrinks to 0, that means it becomes a point, then in that case, you see all the terms will knock out, and finally what we'll have just this equation delta sigma x plus delta tau yx delta y plus capital X is equal to 0. So this gives you the rule of deformation in a sense, that this is the relationship that exists between the stresses for equilibrium in the x direction. So this equation, governing equation, it gives you the involvement of all the stresses acting in the x direction. So this is equation number 1. So equilibrium equation 1. Exactly in the similar manner, if you try to consider the equilibrium in the y direction, there you see you will have this stress acting in the positive y direction, acting on the face delta x multiplied by t, and then bottom face the stress is acting in the negative y direction, and this is actually what is in the negative direction. And similarly, the stresses tau xy is going to be forces in the vertical direction, vertical y direction, and therefore you see this is due to shear stress on the right hand face, x face, and this area is delta y into t, and on the left face, the shear stress is tau xy multiplied by delta y into t, and the body force, which is going to give also a force in the vertical direction, which is capital Y per unit volume multiplied by volume delta x delta y into t. And again, as we simplify, considering the situation that we are trying to obtain equilibrium condition at a point delta x, delta y sinks to 0, then in that case, you see, finally we get this equation, and this equation gets simplified. Tau x, delta tau xy delta x plus delta sigma y delta y plus capital Y equal to 0. So it is the similar form as in equation 1. So this is the equilibrium of stresses, equilibrium equation involving stresses in the y direction. So this is the second equation involving the three stresses. Now coming to think of it, we have actually two stresses, shear stress tau xy and tau yx. Let's see how they are related. Now obviously when a body is in equilibrium, it will have equilibrium in all the three sense, in the sense that it will have, just look at this, you will have equilibrium in the x direction, you will have equilibrium in the y direction. You should also have no rotation because the body is not rotating. You see, when it is deforming, we just constrain its rigid body rotation. Every point is going to have rotation because of the deformation. And therefore, these boundary stresses which are acting, they must also give rise to moment equilibrium. There should not be any rotation of this element because there is nothing that which is externally acting. So therefore, you see, all these stresses which are acting on the boundary of this element, when you try to take its moment above the center point P, you will find that this equilibrium equations, it is quite simple thing. I will just try to explain to you. So when you try to take delta x to be 0, so therefore you see that stress on the left face is going to be sigma x, stress on the right face is going to be sigma x, delta sigma x will knock out. And that is therefore the total force acting on the left vertical face is going to balance with right vertical face. And their total force will pass through the center point. You see, total of the vertical force acting is going to be actually at the center. Total of the vertical force on the left x face is also going to be at the center, and therefore they are going to pass through the point P. And now look at this. What is the other thing? You see, you have the tau xy stress on the left vertical face acting downward, and on the right vertical face, you are going to have stress tau xy plus delta tau xy. But as delta x tends to 0, this increment shrinks to 0, and therefore, see, these two stresses which are acting parallel, and they are separated by a distance of delta x, and therefore the moment of this force is tau xy multiplied by delta y into t, and this is also tau xy multiplied by delta y into t, and they are acting at a distance of delta x. So therefore the moment is going to be tau xy multiplied by delta x delta y into t in the anti-clockwise direction. Exactly in the same manner, if you try to consider this stress tau xy plus delta tau xy acting on the vertical vertical phase, or rather y phase, positive x y phase, it is acting in the positive x direction, and the stress which is acting on the bottom phase is tau yx acting in the negative x direction. So therefore, see, these two are parallel stresses acting in the x direction, and therefore where delta y tends to 0, this stress is tau xy, and bottom phase is going to have stress tau xy. Both are the same, and it is separated by a distance of delta y. Therefore, moment of these stresses are going to be delta tau yx multiplied by delta x into t, and moment is tau yx multiplied by delta x delta y into t. So the moment which is acting in the negative direction was tau xy multiplied by delta x, delta y into t, and the moment which is acting in the clockwise direction is tau yx multiplied by delta x, delta y into t. And you see, one is acting anti-clockwise, other is acting clockwise. So therefore, these two moments must balance. And once you try to look at that, so what is that condition? You see, it is shown here. So this is what is shown. You see, finally, what it means? It is going to show that this is going to, second term is going to knock out, and finally you see that this moment is equal to this moment, and rest of the terms are 0. Finally, it has tau xy multiplied by delta x, delta y into t, and this is tau yx multiplied by delta x into delta y into t, and this cancels out. Finally, we find that tau xy equal to tau x. So that's what it is. That the stresses, when you are talking about the stresses at the shear stresses, you see, you have a quite typically very interesting point that for an element, when you are trying to talk of an element like this, when you try to think of a small element enclosing the point P, then the stresses acting at a point are going to be the sigma x, sigma y, and tau xy and tau yx. But fortunately, what we find that these two stresses are complementary. Tau xy is equal to tau yx. Always you will find in stress analysis that the stresses acting on the two faces adjoining normal faces, they are going to be the same. They cannot be different. These two stresses are the same, so also these two stresses are the same. So this is the typical of stress analysis in 2 dimensions. Exactly same thing can be actually extended to 3 dimensions, and you will come to conclusion that although we talked about 9 stresses, finally shear stresses are 3 independent shear stresses: tau xy, tau yz, tau zx. Therefore, we have 3 dimensions, 6 unknown: sigma x, sigma y, and sigma z, and shear stresses are tau xy, tau yz, and tau zx. So this is it. So finally, I think it is hello. Hello.
Sir, did you get a phone call?
No, it's okay. It's
no problem. Please continue.
It's just a faltu call.
Achha,
anyway, so I hope the participants are actually understanding, or am I fast or am I slow?
No problem. It's perfect, sir.
It's okay. So thank you.
Yeah, it's okay.
Yeah, these business calls are there. Yeah. So finally, let me summarize what we talked about equilibrium equations. So equilibrium equations for 2 dimensions. Finally, that stresses that we have to determine in 2 dimensions are just 3 stresses: sigma x, which is a function of x and y; sigma y is a function of x and y; and tau xy. So these 3 stresses, and look at this. These stresses are actually functions of space x and y. So functions of x and y, and therefore you have to determine 3 functions, and to determine the 3 functions, you have what are the relations that you have to make use of. Finally, you have 2 equilibrium equations. You have 2 equilibrium equations. That is, first equilibrium equation is delta sigma x, delta x, plus delta tau yx, delta y, plus capital X is equal to 0. And second equilibrium equation is going to be delta tau xy, delta x, plus delta sigma y, delta y, plus capital Y equal to 0. You have to determine 3 functions. 3 functions of space. You see, you have to determine 3 functions of space x and y, and you have two differential equations. Wow, what is this? You have the problem that deformation of a body is governed by two differential equations, but you have to determine three unknowns to find out the state of deformation at a point. So it's actually, you have three unknowns but two differential equations. Can you determine? Differential equations are not equilibrium equations. So what is the state? Can you find out? Can you just tell me what is the state? You have come across such situations in stress analysis or solid mechanics or strength of materials. See, you have this sort of problems also in strength of materials. You remember the case that if you think of a rod which is fixed at both the ends, subjected to a load at a point somewhere in between the two ends, and you want to determine the reactions at the ends. So what happens? If you are trying to think of it that two ends are fixed between two fixed walls, and then you are subjecting it to a force at some point in between to the right-hand directions, then in that case you see that you have a situation of finding out the reactions at the two ends, which is coming out from the interactions with the two end walls. And therefore, you see, in this case, you know that the load point is moving, one single point is moving, and you want to find out the reaction forces at the walls. So here in EC, you have to find out two reactions given a single external load. What is this situation? Have you come across this situation? Hello? Anybody? So look at that.
Sir, I think
Yeah,
they are not actually generally commenting. So
okay. Look at this. No, this is okay. Look at this. Please look at this. What I talked. I talked about a component A, B, which is fixed between the two end walls. One wall is at A, another wall is B. They are rigid, and now you are applying a load P. So obviously, you see that when you are actually applying the external load P, obviously this point P is moving in the loading direction or along the load line. On the other hand, you have reactions forces at the wall at A and at the wall at B. So this, if you try to actually show the free body diagram, you look at this, you have the body AB and its reactions that is coming out from the left wall is RA, and the wall at B is giving the reaction RB, and you have the external load P actually. So therefore, you see, you have, if you try to consider equilibrium, obviously it is obvious that this RA and RB are the two reactions, and therefore it is in equilibrium with the external load P, and you write simply the equilibrium equations which is there, RA plus RB equal to P. So you have one equation, but to determine two unknowns RA and RB. So these are actually, this is a statically indeterminate problem. Two unknowns, one equation. So therefore, how did you overcome this? How did you overcome? So you had to, see, if you try to write the, you just try to segregate this body, write the free body diagram. This is what the free body diagram. Now let's isolate, or let us actually break this body AB into two segments. You see, if I break this body into two segments, AC on the left and CB on the right, look at this. So the force acting at the left end is RA, and therefore the right end is also going to be RA, and the right element CB, which is shown there, the force at the right edge is RB, so that's acting, and obviously the force which is going to act at C is going to be RB. So therefore, you see, what we are going to get, we are going to get that RA plus RB is equal to total external force P. Alternatively, RA plus RB equal to P. Now, how do we determine the forces? How do I get one extra equation have the problem of indeterminacy overcome. What is that? If we try to talk about that, this point C would have a displacement of common displacement. You see, this point C is going to move to the right. If I say that for the left element, this edge is going to move by distance u1, and this right element, it is also going to move by some displacement, that is u2. Now, what is that constant in this displacement process? Obviously, we know that C is going to move by the same distance. And therefore, this U1, which is the deformation of AC, and CB has deformation U2, these two U1 and U2 must be same. And this is called constraint condition, compatibility condition. So therefore, the displacement of the segment AC, displacement of the segment AB, U1 and U2, they are same. And therefore, this is called compatibility condition. Constraint condition, the deformation that is constrained, that can be also used to find out an extra equation. Look at this. Therefore, here you see, if you write the deformation of segment AC, it is U1 is nothing but RA, length of AC divided by area cross section multiplied by modulus E. Similarly, U2, displacement of the segment CB is nothing but RB into LCB divided by AE. And this compatibility equation is nothing but U1 equal to U2, and which gives you an equation, you see, RA into LC by AE equal to RB into LCB divided by AE, and which gives you a condition, linkage between the two forces RA and RB. You had the equilibrium equation, which is there right at the top. You see, that equation is going to give you RA plus RB equal to P1 equation. And now this displacement constraint condition, compatibility condition, gives you a relationship between the two forces RA and RB. So therefore, you see, you have two unknowns, RA and RB, and you have now two equations, RA, and this is equation A and D, two equations. So therefore, you see, you are in a position to determine two unknowns, and the statical indeterminacy which was there is overcome. So here you see that you bring in compatibility condition to overcome the statical indeterminacy. In fact, what we have in the case of stress analysis, to exactly the same condition, you see, same situation we have. Look at this. What I was talking little while ago, that look at this one, these two governing equations that we have got finally for equilibrium considerations, that is actually equation 1 and 2. So this is equation 2, and the equation 1 is actually written a little earlier. So therefore, equation 1 and 2 are the two equations. This is equation 1, and then we have got the equilibrium equation in the y direction, which is written there. So therefore, you see, these two equilibrium equations, and we have three functions, sigma x, sigma y, tau xy are to be determined. So therefore, we have three unknown functions, but we have two differential equations. So therefore, the problem is statically indeterminate. Statical equilibrium equations cannot help us to solve for the three unknowns. So this is the problem, same as in the case of that rod being subjected to loading at a point in between, and it is constrained to move at the ends. So this is it. So therefore, we have statically indeterminate problem, and we have to find out some way to get another extra equations on top of this equation 1 and 2 so that we can solve it. So we'll talk about that. So before we could do this, you see, that we could do this, we have to define the deformation at a point. Deformation at a point. So if we now consider that in 2 dimensions, see that we have two displacements, x and y displacement. And if we try to think of it at a point, I will have displacement in the x direction and y direction. So therefore, you see, that I was actually showing you here. So at every point, you have displacement x, I beg your pardon, x displacement is represented as u, which is a function of x and y. Similarly, y displacement is v, which is a function of x. So these are two displacement functions. Obviously, these two displacements, if you try to write your equations in terms of these displacement functions, your statistical indeterminacy will be gone. So if you want to find out the displacement function, you have two displacement functions, and I'll show you within a couple of minutes that you can write the differential equations in terms of these two displacements, as in the case of that one-dimensional strength of material problem. We wrote the equation in terms of displacement. The displacement of the common point was u, and that u is determinable because the displacement has linkage, segment left, segment right, they have the same displacement u. So if I could determine u, which is nothing but u1 and u2, I can solve the problem, because the force on the left end or segment was related to the displacement, force on the right segment was also related to the displacement. So that's how it is. So therefore, we'll now show you exactly the same way that this differential equation that we have written involving the three stress functions, sigma x, sigma y, tau xy, I can write them differently. So let's now write some of the other things. We'll have to define strains. As we have defined stresses, displacements u and v, I can write them in terms of strains also. Strains are three strains that occurs at a point. Epsilon x, linear strain in the x direction, is nothing but delta u delta x. Epsilon y, linear strain in the y direction, is delta v, its derivative with respect to y. And shear strain, it's nothing but cross derivative u displacement delta u delta y plus delta v delta x. So these are the three strains. Like stresses, sigma x, sigma y, tau xy, here strains are also three: epsilon x, epsilon y, and gamma xy. And it is easy to show that if you just try to write this, take this relation gamma xy, this gamma xy, you see, if you try to take derivative of this left hand side twice, once with respect to x and second time with respect to y, you get this linkage. Delta 2 gamma xy, delta x delta y is equal to delta 3 u delta x delta y square plus delta 3 v delta y delta x square. So this is actually the constant. Although we have three strains, but then they have constant. This constant equation is this. So that's what it is. See, you have three strains, but then you have a constant between these three strains. This is what is known as also compatibility conditions. Three strains are linked; they are not independent, and this is delta 2 gamma xy, delta x delta y is equal to delta 2 epsilon x delta y square plus delta 2 epsilon y delta x square. This is the compatibility condition. As in the case of that strength of materials problem, what are that compatibility? U1 equal to U2, and here this equation 3 is the compatibility conditions of deformation in two-dimensional elasticity. Now let's see how can compatibility equations I can make use of to find out extra equations involving the stresses. You see, in the case of that strength of materials problem, I had two unknown forces, RA and RB, and I had one equation, equilibrium equations, but I did get another extra equilibrium equation from the consideration of compatibility, that U1 equal to U2. And exactly here also, you see that you had three strains, but when you try to write the constant amongst them, it gives you this equation number 3, which is compatibility condition. I'll now try to show you that this compatibility condition in the case of strength of material problem is U1 equal to U2. Finally, it gave us linkage between RA and RB. Now, I'll make use of this equation 3 and I'll show you that I can get an extra linkage, extra equations involving this particular equation involving the 3 stress functions sigma x, tau xy, and sigma y, or sigma x, sigma y, tau xy. I'll show you that in a couple of minutes. Look at this, generalized Hooke's law. So this must be considered. The deformation process is governed by generalized Hooke's law. So when you try to consider an element with the stresses sigma x, sigma y, and tau xy, then you see in that case, the deformation, the strain that comes up in the x direction, linear strain, it is epsilon x. It's nothing but sigma x stress acting in the x direction. It will give you strain sigma x by E, and sigma y, it is also going to give a cross action in the x direction, which is given by this relationship using Poisson's ratio. So when you are stretching it in the y direction, it contracts in the x direction. Exactly the same way when you stretch it in the x direction, it contracts in the y direction. So that's what is shown here. Epsilon x, it gives you linear strain sigma x by E minus nu times sigma y by E. That nu is Poisson's ratio effect, cross effect. So epsilon x is given by this, epsilon y in the same manner, sigma y by E minus nu times sigma x by E. So this is Poisson's ratio effect, and it gives you the Hooke's law products. And what about the shear strain? Shear strain tau xy is given simply by tau xy divided by G. And G is the rigidity modulus and E is the elastic modulus. So therefore, finally, you see, these equations that I have written, it can be actually inverted. You can write the stresses in terms of strain. So if you make use of these 3 equations which are written here, and if I try to obtain sigma x, sigma y, tau xi in terms of these 3 strains, we get finally this. That sigma x is equal to E by 1 minus nu square into epsilon x plus nu epsilon y. Sigma y is E by 1 minus nu square into sigma y, I'm sorry, epsilon y plus nu times epsilon x. And shear stress is nothing but G into gamma xi, where G is rigidity modulus, already have introduced. So finally, you see, the strain that comes up because of the stresses acting sigma x, sigma y, and tau xi gives rise to shear strain only, deformation, and sigma x, sigma y gives the strain, contraction or expansion. Please, sigma x and sigma y gives you contraction or expansion, whereas tau xi gives you just deformation. A body which is initially rectangular, it will not rectangle, it will become deformed into slightly like parallelogram, and it is going to be actually shear difference. And therefore, you see, thus, when you are having normal strain in the x direction, y direction, if you think of the z direction, you will have also Poisson's ratio effect. And that Poisson's ratio effect, if you want to find out the strain epsilon z, contraction or expansion in the z direction, is going to be given by nu times sigma x plus sigma y by E. So if you don't have any sigma z is 0, but there will be contraction. You can have that eliminated. So finally, these 3 relations I can write: sigma stress, sigma x stress, sigma y stress, tau xi stress is going to be actually given by this E by 1 minus nu square into that matrix whose terms are 1 nu 0, nu 1 0, 0 0 1 minus nu by 2 multiplied by 3 strains. So this matrix E by 1 minus nu square into that rectangular matrix is written as D matrix. It is called stress strain matrix, and this epsilon 3 terms are written as strain matrix. So therefore, stress matrix is equal to stress strain matrix multiplied by strain matrix. So this is also in short form, and this is the relationship for stress strain relationship under conditions where sigma z is 0. It is called plane stress condition. Plane stress condition. No stress in the z direction. Alternatively, you can have a situation. Please note that I am now showing an element wherein the stresses are acting on the x, y axis, plus at the same time there is a stress acting in the z direction, sigma z. In this case, sigma z is externally acting. So under these conditions, if you write the strains in the normal strains, it will involve all the three normal stresses. Epsilon x is sigma x by E minus mu sigma y by E minus mu sigma z by E. Similarly, epsilon y also in the same manner is written. Epsilon z is written in the same manner using the generalized. And shear strain, shear deformation, gamma xy is tau xy shear stress divided by rigidity modulus G. And in this case, you see, you can have a situation that if you try to write, you can have two situations. You see that you can allow the deformation to take place in the z direction. So you can have a situation where the z stress is applied, and we would like to consider a case wherein there is no strain because sigma x and sigma y is going to produce contraction in the z direction, but this sigma z stress is applied to prevent that contraction. Again, I repeat, sigma x and sigma y will expand the volume of the element in the x and y direction, but it will try to reduce the volume in the z direction. But if you want a situation that this z direction, it should not have any contraction whatsoever, we want a situation wherein epsilon z strain is 0 in the z direction. So you see, if you want to have that, then in that case we can find out that this sigma z is going to be related to sigma x and sigma y. If you write this last equation of strain epsilon z relationship, put that equal to 0, it gives you that sigma z that is to be applied externally is dependent on sigma x and sigma y multiplied by Poisson stress. So this situation wherein you want to eliminate contraction in the z direction, then you will have this condition is known as plane strain condition. The body deforms only in its own plane. It does not have any deformation in the perpendicular direction. That's why it is plane strain. And in that case, you must apply load in the z direction, which depends on the local stress sigma x and sigma. Finally, therefore, we'll have through inversion epsilon x and epsilon y in terms of sigma x and sigma y, and tau gamma xy is given in terms of tau xy. And finally, if we write the stress matrix, it is going to have this stress strain matrix multiplied by strain matrix. And this stress strain matrix, it looks like this: E by 1 plus mu into 1 minus 2 mu, and the matrix inside is 1 minus mu, mu 0, and mu 1 minus mu 0, 0, 0, 1 minus 2 mu by 2. So that's what it is. And this is the stress strain relationship in the case of plane strain. So that's how we find that strains are related to the stresses in 2 dimensions. So it depends only on three stresses: sigma x, sigma y, and tau xy. Please, I want to summarize that this stress strain relationship that we have got, it gives you one common point that the three stresses are not actually, the 4 stresses are not actually going to be independent. We have a case of just in 2 dimensions. If it is plane stress, stresses are related to the strain, 3 strains are related to the 3 stresses. In the case of plane strain, you have the 4 stresses, sigma z is there, but it is a function of sigma x and sigma y. So finally, again in plane strain also I have 3 unknowns: sigma x, sigma y, and tau x. So that condition we have come for both these situations. Now let us see. Let us see that we had already actually the compatibility conditions that we had written gamma xy is equal to delta 2 delta y square epsilon x plus delta 2 delta x square epsilon y. You know, that's the under plane stress condition, the compatibility conditions. So if we now write this compatibility condition, it looks like this: 2 into 1 plus mu delta 2 tau xy delta x delta y delta 2 delta x square sigma y minus mu epsilon x plus delta 2 delta y square sigma x minus mu sigma. So therefore, this is the compatibility conditions. So therefore, you see that what we have got, we have three stresses to determine: sigma x, sigma y, and tau xy. Whether it is plane stress or plane strain, we have three unknown stress constants: sigma x, sigma y, and tau xy. And finally, you see, we have three conditions. We have first equilibrium in equations involving sigma x, tau xy. Second equilibrium equation involving tau xy and sigma y. So therefore, we had two equilibrium equations plus and one extra condition here, which we get from compatibility, which is shown here. It is equation number 5, last equation. So therefore, you see that we have two equilibrium equations plus some constraint on the deformation, this another equations involving the three stresses sigma x, sigma y, tau xy. So therefore, you see that exactly in the case of strength of material problems, we had two unknowns, one equilibrium equation, one compatibility conditions. In the case of two-dimensional stress analysis, we have three stresses as unknown. We have two equilibrium equations plus one constant conditions or compatibility conditions, which is also involving the three unknown stresses. So therefore, our problem is solved. So we have three stress functions which are related by compatibility conditions, and therefore you see you have the problem of indeterminacy gone. So if you work in terms of the this, if you make use of the compatibility conditions, you get the exact equation to get over the statical indeterminacy. Now I want to actually tell you one more thing, that compatibility condition in the case of strength of material, when we wrote in terms of displacement, then we had U1 equal to U. So there was actually one extra equations, and which when we wrote in terms of the end forces, it was giving linkage between the two end reactions. We will try to do the same thing here. So you see, if we write the compatibility conditions in the strength of material problem, it was U1 equal to U2. And if we wanted to work in terms of the displacement of the center point C, we would have one equation, one unknown. But here in actually see, we have three equations. But now I can show you that if we write in terms of these equations in terms of the strains involving U and V, we'll get two equations involving two unknowns. How do we do that? Look at this. I will go back to equilibrium case. Sigma x, we have just now derived that sigma x is given by generalized Hooke's law E by 1 minus mu square delta U delta x mu times delta V delta y. Sigma y similarly is E by 1 minus mu square into delta V delta y plus mu delta U delta x, and tau xy is nothing but E by 2 into 1 plus mu delta U delta y plus delta V delta x. So let's now write the equilibrium equation in terms of these equations, in terms of the stress, giving in terms of stresses. So if I try to write the first equation, you see delta sigma x delta x plus delta tau xy delta y equal to 0. For let's just for the moment consider that capital X is 0, capital Y is 0. So therefore, the first equilibrium equation, which we write the stresses in terms of the displacement, you see I get first equilibrium equation converted into E by 1 minus mu square delta Tu delta x square plus mu times delta 2 V delta x delta y plus E by 2 into 1 plus mu delta 2 delta y square plus delta 2v delta x delta y. So you see that I get one equation, first equilibrium equation. When I write in terms of the displacements function u and v, I get one equation. Similarly, if I try to consider the second equilibrium equation, this is second equilibrium equation is this. When I substitute the value of sigma x and sigma y in terms of displacements and then simplify, you see I get the second equilibrium equations converted to e by 2 into 1 plus mu delta 2u delta x delta y plus delta 2v delta x square plus e by 1 minus mu square delta 2v delta y square plus mu times delta 2u delta x delta y equal to 0. So I want your attention. Look at this first equilibrium equation is converted into equation 6. Second equilibrium equation is converted into equation 7. Look at these two equations. If you are trying to think of two-dimensional stress analysis, your problem is to determine the displacement at every point for u function, u as a function of x and y, v as a function of x and y. That's it. And now you see that when you have made use of the stress and relations, you get the two equations, 6 and 7, which are involving just u as a function of x and y, v as a function of x and y. So therefore, you get one extra equation to overcome this statical indeterminacy. So that's what it is. See, if you work in terms of displacement, in the case of strength of material problem, u1 equal to u2, so you had to determine simply one displacement u, and here you see, when you try to make use of the compatibility conditions and make use of it, equilibrium equation simply boils down to two partial differential equations of second order involving u and v functions. So that's it. So I again wanted to stress upon one more point. Look at this, when you are trying to work in terms of stresses, you have the equations, equilibrium equations, which are actually first order differentials. But when you try to write in terms of displacements, the order of differential equation is second order partial differential equations. So this is another difference between the two problems. When you try to work in terms of stresses, you get actually 1 degree less first order differential equation, partial differential equations. But when you work in terms of displacements, your differential equation is going to be second order partial differential equations. So that's another difficulty, or maybe actually this is the situation in reality that exists in case of two dimensions. So that's what it is. And I think, we'll stop here for now, and we'll again actually start discussing further on from this point in the next session, which is going to be, I think it's going to start at 4 o'clock. Oh, I'm sorry, it is 3:30.
Yeah, sir, it is going to be at 2:30.
Yeah. I'm sorry.
2:30.
Yeah.
Sir,
so therefore, we are going to start at 2:30. So
yes, sir.
Can we break now, or you want me to continue?
Yeah, one participant wants to ask you a question which I can read for him.
Please.
Yeah, he says that, can you clarify what is statically indeterminate condition and compatibility condition?
Yeah, you see, I hope you have understood the problem of strength of material. Have you understood? If you have understood, there is no difficulty. You see that when you are trying to consider that single, let's say, rod which is fixed between two ends, and it is subjected to loading somewhere in between. So that load point is moving by a single displacement, it is moving by some amount. That's a displacement of the load point. And now, if you try to consider that body to be separated, and you try to segment it in two segments, left segment, it is fixed at the left end and it is subjected to some loading at the right end, or it has some displacement in the x direction, which I said u1. Similarly, if you consider the segment on the right side, it's going to have some displacement u2 towards the load direction. So therefore, you see, the right segment is going to have deformation U2 and left segment would have deformation of the point in the right direction by U1. So what is the compatibility condition? So that both the points are going to have same extent of deformation. So that is the same, that is compatibility condition. The section C is going to move by the same amount, whether it is lying on the segment A or left segment or right segment. So this is same displacement is occurring of that point, whether it is lying on the left segment or right segment. This is compatibility condition. Is that clear? Is that clear? Sachin, can you give me feedback? Is that clear?
Yes, sir. He says yes.
Okay, good. So therefore, that is compatibility condition. And you see that compatibility conditions, I think his question was, what is compatibility conditions, right?
Yes, sir.
And what is the second part?
The second part was, statical indeterminacy and compatibility.
Okay, so compatibility we have understood. Statical indeterminacy, see that in that case of the strength of materials problem, your element, when you try to see its free body diagram, you are going to have that from left to right end the body or that element, and now P is acting from the point C to the right, and you have now reactions at the wall, at the left end some RA and at the right end some RB. So if you want to actually get the total unknown forces, in that case you have to find out the forces acting at the left end and also right end. So you have two unknowns. You see, RA and RB are the two ends. Reaction force at RA and reaction force at RB is RB. So in this problem, you see, external load is P, but you have two unknown reactions RA and RB. And this, from the equilibrium conditions, we find that RA plus RB equal to P. So you have one equilibrium equation, RA plus RB equal to P, and you have to determine RA and RB. So it is statically indeterminate. From the equilibrium equations, which involves both the unknowns, you cannot determine them. And in order to overcome the statical indeterminacy, you have to bring in that deformation conditions that U1 equal to UT. So therefore, this problem is statically indeterminate. From the equilibrium equations, you couldn't determine RA and RB, but by bringing in the displacement conditions or compatibility conditions, you have got some linkage between RA and RB, and then you are able to solve for both RA and RB. So that's what it is, compatibility conditions and statical indeterminate. I hope I am clear now.
Yes, sir. Yes, sir. He says that's fine. Yeah, thank you very much. May I announce the time for the participants? Dear participants, please join back sharp at 2:30 p.m. Professor Maiti will continue with his next session in continuation with his current session. Sir, thank you very much for.
Thanks a lot.
Yeah. Yes, sir. We'll meet again in the afternoon.
Yeah. Thank you.
Yes, sir. Thank you.